Okay, so this is our physics formal lab. So the motivation and context behind this was to determine how different textures of grounds affect the inelasticity or elasticity of collisions. Inelastic collisions, kinetic energy is conserved, and inelastic collisions, kinetic energy is not conserved. Our goal is to determine how much of the ball's kinetic or potential energy is transferred to internal energy for different textured surfaces. Our main findings were that the ball dropped onto the mud had the most inelastic collision, and the ball dropped onto the tile had the most elastic collision. For our experiment, we recorded 3 videos of a ball dropping onto different ground types that we wanted to test, which were grass, mud, and tile. We used the same ball for all of these videos, and the mass of that ball was found using a scale. And we used a meter stick to keep the height that the ball was dropped from consistent, and the same person dropped the ball. We uploaded the videos to Tracker and tracked the ball from the initial drop until the peak of the first bounce, which allowed us to track the velocity and movement of the ball. So for our system schema, this is idealized. In our actual experiment, it is not a closed system, and it is the ball and the ground interacting and gravity acting on the ball. So for our prediction, the ball dropped on the tile would be the most elastic, the ball dropped on the mud would be the most inelastic, the ball dropped on the grass would be somewhere in between the two, and for the ball dropped onto the mud, almost all of the kinetic energy would be converted to internal energy, and most of the kinetic energy for the ball dropped onto the tile would be conserved.
Once we put the data into Tracker, we averaged it across 3 different trials, and we used those to create position versus time and velocity versus time graphs. Those helped us calculate how much energy the ball had at different points. We calculated in Excel using standard error. And then we made qualitative energy pie charts to better understand how the energy was acting across the 3 trials. The first ball dropped on tile. You can see it bounced pretty high up, almost back to its initial starting position. And if you look at the energy pie charts, only a little bit of energy was converted into internal energy. For the ball dropped on grass, it didn't bounce nearly as high as the one on tile, and a little bit more energy was converted into internal energy. And then finally, the ball dropped in the mud. It didn't bounce at all, and all of the energy was converted into internal energy. For our data and analysis, we calculated the potential energy of the ball before the drop and then at the top of the first bounce, and we found the difference, the percent change there. For error, we used different uncertainty equations. And then we found for the tile that 21% of the energy was lost to internal energy, plus or minus 0.6%. For the grass, we found that 56% of energy was lost, plus or minus 4.4%. And then for the mud, we found that 100% of energy was lost to internal energy, plus or minus 1.3%.
So to minimize error, we tried to keep everything as constant as we could between all 9 trials. So we used the same ball and meter stick, and then we had the same person drop the ball and the same person record every time. We also only used the best videos, which were the ones where the ball bounced to about the same height every time. So throughout all of this, energy, velocity, and momentum was not conserved. So real-world collisions cannot be perfectly elastic, as some energy is always lost, so that's why none of it was conserved. So between all of the different texture of grounds, some energy was going to be lost due to air resistance and the sound of the ball hitting the ground. So that's the only place where energy was really lost for the tile. For the grass, there was also some more energy lost to the ball sinking into the grass because it's squishier. And then the rest of the energy that was lost for the mud was because of the mud being squishier. So the mud absorbed all the energy because the ball didn't have enough to bounce back out. Some potential sources of error was inconsistent camera angle because someone was holding the camera, we didn't have it set up. Direction of the bounce because it didn't always bounce perfectly straight as the ground was not completely flat and level. We went outside for the grass and mud trials. Any wind could have blown the ball slightly. And then data was averaged across 3 trials, so any differences there are error. Overall, our predictions were very similar to the data we collected, so we had it pretty much right for the tile and the grass. For the mud, we thought there would be a slight bounce and not a complete energy conversion to internal energy, but it did completely transfer, so we were off there. And then we could improve our experiment by using a tripod when recording, taking even more videos to really only get the best ones, finding even flatter and level ground, and then taking more trials, so averaging data across more videos.